So we're going to talk now about the role of area in the normal density function. So the normal probability density function remember, one of the ways we said probability density or probability distributions could be given was as a mathematical formula. Well, here is that mathematical formula. So this is very complicated looking. Again, the only reason I'm showing it to you is not to make you panic. It's just to let you know that yes, there is actual math behind this. It's not just, the calculator randomly pulling numbers out of thin air. So we can't do anything with this unless we know some fairly complex calculus. Which is why, again, thank goodness we have calculators that are so smart now. So the area under the normal curve for any interval of values of the random variable x represents either the proportion of the population with the characteristic described by the random variable, or the probability that a randomly selected, now it's important that it's randomly selected individual from the population has the characteristic. So let's draw the curves for a couple problems, shade our relative area that they're asking us to find. This is very important. I cannot stress enough to you. Draw your pictures, draw your pictures, draw your pictures. It will help you get things in the calculator correctly. Now, a good chunk of you will probably ignore me. That's usually what happens. And that's fine. I've told you to draw your pictures for help, but if you choose not to do it, that's your decision. So let's look at this example. The lives of refrigerators are normally distributed with a mean of 14 years and a standard deviation of 2.5 years. So let's draw the curve, label the parameters, and shade the region that represents the proportion of refrigerators that last for more than 17 years. So more than 17 years is the region we want. So here's our picture. And these don't have to be perfect, obviously. I usually draw my curve and then my axis. It's so much easier. So straight down from the middle is our mean, which is 14. And since our standard deviation is 2.5, we're going to add 2.5 going to the right and subtract it going to the left. So when we do that, we get 16.5, 19, and 21.5. Going the other way, we have 11.5, 9, and 6.5. So we want to shade the region that is the proportion of refrigerators that lasts for more than 17 years. So, I don't know, 17's about right here. Doesn't have to be perfect. And we should label that. So, 17. And we need more than 17 years. So that's greater than, we shade to the right. So this is the picture we would draw for this problem. Now, we'll learn in the next section how we actually figure out that area. But suppose the area of the shaded region is 0.1151. Write two interpretations. So interpretation number one is, remember there's two ways. It's either the proportion of the population or the probability that a randomly selected individual from the population has the characteristic. So in this case, the first one, interpretation is the proportion of refrigerators that last more than 17 years is 0.1151. Interpretation number two is the probability that a randomly selected, and remember randomly selected is important, so the probability that a randomly selected refrigerator lasts more than 17 years is 0.1151. Or you could also change that decimal into a percent. In Pearson, be careful to pay attention to whether it wants as a decimal or as a percent. Usually if it wants a percent, it'll have a little percent symbol after the answer box. Okay, so I think you guys should try this second problem on your own. Pause the video, and then when you think you've got it, start the video again to see if you are correct. So in this example, it says the length of human pregnancies are normally distributed with a mean of 266 days and a standard deviation of 16 days. Draw the curve, label the parameters, and shade the region that represents gestation times between 250 and 298 days. So here's our curve. I mean, again, not the best, doesn't matter, close enough. As long as everything's labeled, we are good. So the mean is 266 days. And our standard deviation is 16. So that gives us, going to the right, 282, 298, and 314. Going to the left, it gives us 250, 234, and 218. So remember, just add 16 to go to the right and keep subtracting 16 to go to the left from the mean. And we need the area between 250 and 298 days. So here's 250 days. Here's 298. Since those are actually on tick marks, we don't have to label them separately, but we will shade this area between them. So that's the region that we would be looking for the probability for. Again, we'll learn how to actually find this probability using the calculator in the next section. But for now, let's just interpret it. So, suppose that shaded area is 0.815. Provide two interpretations. So, number one, the proportion of human pregnancies that last between 250 and 298 days is 0.815. Our second interpretation is the probability that a randomly selected human pregnancy lasts between 250 and 298 days is 0.815. That concludes our discussion of section 7.1 and our beginning talk on continuous probability distributions. We will pick up in section 7.2 in the next video with how we actually find these probabilities.